The concept of the edge of the universe is a cosmic riddle, one that shifts and twists the moment you think you grasp it, transforming from a simple boundary into a profound philosophical and scientific conundrum. It's not a wall or a fence, no grand celestial barrier beyond which lies, well, nothing. Instead, the edge we often speak of is a horizon, a limit not of space itself, but of what we can see, an intricate interplay of time, light, and the very fabric of space-time. Imagine yourself at sea, standing on the deck of a ship. The horizon seems to be the very edge of the world, a definitive line where the sky meets the water. Yet, even as you gaze at that seemingly final boundary, you intuitively understand that the ocean continues far beyond it, stretching on, mile after unperceivable mile. Our universe is much the same. We live within what cosmologists term the observable universe, a vast cosmic bubble spanning an incomprehensible 93 billion light-years across. This bubble represents the furthest light has had time to travel to us since the universe's fiery genesis, the Big Bang, roughly 13.8 billion years ago. The crucial phrase here is, has had time to travel. Light, despite its astounding speed, is finite. The light from a galaxy 15 billion light-years away simply hasn't reached us yet, and so, that galaxy remains outside our observable horizon. The ultimate visual frontier of this observable bubble is marked by the faint, ancient whisper of the cosmic microwave background, CMB radiation. This is the afterglow of the Big Bang, a primordial light that began its journey across the cosmos when the universe was merely 380,000 years old, cool enough for photons to travel freely. It's like staring into the infancy of the cosmos, seeing light that has journeyed across billions of years, stretched and reddened by the universe's relentless, accelerating expansion. Every point in the universe, every galaxy, every star, theoretically has its own observable bubble, its own unique horizon, making our edge a subjective boundary tied to our specific location and the passage of time. As the universe ages and light from more distant regions reaches us, our observable universe slowly, incrementally expands. But what lies beyond this observable sphere? This is where the true mysteries begin to unfold, and where scientific consensus butts up against theoretical speculation. The most widely accepted cosmological model suggests that the universe simply continues. There's no scientific reason to believe space suddenly stops, as if hitting an invisible wall. Our universe, according to current observations of the CMB and the large-scale structure of galaxies, appears to be remarkably flat, suggesting it stretches on and on and on infinitely, or at least far beyond the scales we can ever hope to probe directly. It's an expanse without end, a cosmic tapestry woven without a final stitch, filled with more galaxies, more stars, more cosmic wonders, repeating patterns, or entirely new configurations, far beyond what our most powerful telescopes can ever hope to glimpse. Yet, even this mind-boggling concept of an infinite universe raises more profound questions that push the very boundaries of our understanding. If the universe is truly endless, then could there be other universes, perhaps with different physical laws, born from different Big Bangs in a vast multiverse? This idea is championed by theories like eternal inflation, where our universe is but one bubble in an ever-inflating larger cosmos, or the many worlds interpretation of quantum mechanics, where every quantum possibility branches off into a new, parallel universe. Could our entire reality be just one of countless bubbles floating in an incomprehensibly larger cosmic foam, each with its own unique history and set of fundamental constants? These are the theoretical frontiers, where the edge of our understanding blurs into the realm of pure speculation, fueled by the tantalizing hints from quantum mechanics, string theory, and the very fine-tuning of our own cosmic parameters. Furthermore, the edge can also be understood as a temporal boundary. What was before the Big Bang? If space-time itself began with the Big Bang, then before has no meaning in a conventional sense. This leads to concepts like cyclic universes, where a big crunch is followed by another Big Bang, or the idea of our universe being a brain, colliding with another brain in higher dimensions, sparking a new creation event. These are not edges in space, but edges in the very fabric of existence, questions about the ultimate origin and fate of reality itself. The edge of the universe, then, is less a physical place we could ever reach and more a dynamic, evolving conceptual boundary, a testament to the limits of our perception and the potentially boundless nature of reality itself. It's a constant invitation to wonder, a powerful engine for scientific inquiry, and a profound reminder that the universe, even in its observable immensity, is but a fraction of a grander, more mysterious whole, forever pushing the boundaries of what we can imagine and urging us to seek further, to learn more, and to embrace the humbling vastness of the cosmos. Knowing the edge of the universe isn't like encountering a physical border on a map or a fence you can touch. Instead, it's about understanding the fundamental limits of what we can observe and consequently what we can know about the cosmos, governed by the immutable laws of physics and the universe's own history. The cornerstone of this understanding is the finite speed of light. Light, the fastest thing in the universe, travels at an incredible yet fixed speed. This means that when we gaze out into the depths of space, we are inherently looking back in time. The light from a galaxy 10 billion light-years away isn't showing us that galaxy as it is today, but rather as it was 10 billion years ago when that light first embarked on its epic journey across the vast cosmic ocean to reach our telescopes. Our universe, as best determined by numerous observations and calculations, began approximately 13.8 billion years ago with the Big Bang. This age sets an absolute limit on what we can possibly see. Light from anything further away than what could have possibly traveled to us in 13.8 billion years simply hasn't arrived yet. This defines our observable universe, a cosmic sphere with us at its center, representing the furthest light has had time to reach us. The most profound piece of evidence for this edge is the cosmic microwave background, CMB, radiation. Imagine the early universe, for its first roughly 380,000 years, as an incredibly hot, dense fog, a plasma of charged particles like protons and electrons. Photons, particles of light, couldn't travel freely. They were constantly scattering off these charged particles, making the universe opaque. It was like being trapped inside an infinitely dense cloud where you couldn't see anything clearly. As the universe expanded, it cooled. When the temperature dropped to about 3000 Kelvin, electrons finally combined with protons to form neutral hydrogen atoms. This pivotal event, known as recombination or decoupling, dramatically changed everything. With electrons now bound within atoms, photons were liberated. They could finally travel freely through space without constantly bumping into charged particles. This first light that was set free is what we observe today as the CMB. It's an almost perfectly uniform glow of microwave energy permeating every direction in the sky, a fossilized echo of the universe's infancy. We cannot see beyond the CMB, because before that point, the universe was simply too opaque for light to travel through. It acts as a kind of wall of light, marking the earliest moment we can visually detect. Crucially, the universe hasn't been static since the Big Bang. It has been continuously expanding. This means that the regions of space that emitted the CMB radiation we observe today were much, much closer to us when that light first left them. Over the intervening 13.8 billion years, the space between those regions and us has stretched significantly. Through sophisticated calculations incorporating the universe's expansion rate, described by Hubble's law, cosmologists estimate the current physical distance to the particles that emitted the CMB to be approximately 46.5 billion light-years in every direction from us. This larger figure, often called the co-moving distance, accounts for the expansion of space itself that has occurred during light's long journey. So, while the light we see is 13.8 billion years old, the sources of that light are now much further away due to the universe's growth. Therefore, we understand the edge of the observable universe not as a fixed barrier in space, but as a dynamic horizon defined by the speed of light, the age of the cosmos, and the fundamental transparency of the early universe. It's an observational limit, a boundary to our current knowledge, rather than a physical end to the universe itself, which is widely believed to extend far beyond what our most powerful instruments can ever hope to perceive. The edge of the universe, while not a physical boundary, but rather the limit of our observable cosmos, holds immense importance for cosmology and our understanding of existence. Its significance stems from several key aspects. Firstly, it provides the empirical foundation for the Big Bang Theory. The cosmic microwave background, CMB radiation, which defines this observable edge, is the most compelling evidence for the universe's hot, dense beginning. By studying the incredibly faint temperature fluctuations within the CMB, scientists can reconstruct the universe's early conditions, its composition, how much ordinary matter, and dark energy it contains, and its geometry, whether it's flat, curved, or spherical. Without the CMB, our understanding of cosmic origins would be largely speculative, lacking the direct observational proof that grounds our current cosmological models. Secondly, the existence of an observable edge highlights the finite nature of our perception and influence. The fact that light has only had a finite amount of time to travel to us means there are vast regions of the universe, potentially infinite, that are fundamentally beyond our direct observation. This limitation is a constant reminder of the humility required in scientific inquiry. It teaches us that our understanding of the entire universe is built upon extrapolations from the observable part, and that future discoveries might reveal phenomena or structures that currently lie beyond our cosmic horizon. This awareness prevents us from making premature assumptions about the universe's ultimate size or contents. Thirdly, the properties of the observable universe, particularly its uniformity and flatness, offer crucial insights into the overall nature of the cosmos. The CMB is remarkably isotropic, uniform in all directions, suggesting that the very early universe was incredibly smooth. This uniformity, combined with observations indicating that our observable universe appears geometrically flat, strongly supports theories like cosmic inflation. Inflation proposes a brief, incredibly rapid expansion of the universe in its earliest moments, which would naturally smooth out initial irregularities and flatten its geometry. Thus, studying the edge helps us validate or refine theories about the universe's earliest fractions of a second, addressing fundamental questions about why the universe is the way it is. Finally, the concept of the observable edge also informs our understanding of the universe's expansion and its ultimate fate. By examining how the light from distant galaxies at the edge has been stretched, redshifted, by the universe's expansion, we can accurately measure the current expansion rate and even discover its acceleration, attributed to dark energy. This allows us to project forward and hypothesize about the universe's future, whether it will expand forever, eventually contract, or experience a big rip. The edge acts as a cosmic window into the past, allowing us to trace the universe's evolution and make informed predictions about its distant future. In essence, the edge of the universe is not a barrier, but a powerful observational tool. It's the furthest legible page in the universe's autobiography, providing indispensable clues about its birth, evolution, composition, and potential destiny, all while humbly reminding us of the immense cosmic mysteries that still lie beyond our grasp.